Yeah, so good morning. Felix, Bettonvil, Leiden University, werkgroep Meteoren. My topic today will be indeed influence of weather data on the fireball's dark flight. As starts all with some Python code which we made available, and as soon a fireball, especially big fireball, appears, you want to use that. And one of the inputs which is not standard available is some atmospheric data which you need. And what is that? So here is the equation of motion of a dark flight, and where we speak about are in purple the wind components, horizontal in the direction of flight and perpendicular to it, and in blue the density of the air, which you need to know as function of height, and the density of the air you can compute if you know the pressure at that altitude and the temperature. So that's what you want to have. And you want to have that quickly because that fireball just happened and there might be a meteorite somewhere. So that sounds all very trivial, and I tried to look a bit deeper into that. And so here is what you all can think of. Most logical is weather balloons or weather models. There is also a spacecraft, Aeolus, but that's just decommissioned, and number 2 is still in the planning phase, so we do not have to look into that. We have also not to look into Doppler radars, which are great, but we have no access to them in the Netherlands, and they also probe the lowest part of the atmosphere. So let's go a little bit into details. If we think about weather balloons or sounding balloons, they give as a function of altitude, temperature, they measure the pressure and the wind components and the wind direction, and that is widely available on the internet. They have usually very good height or altitude resolution. But there's also downsides. They usually don't fly at the moment that the fireball appears, and also not at the location where the fireball is. So everything is a little bit different. Then as a second option, we have models. Of course, we have models because there are weather forecasts being made. And ECWMF is a good example, or GFS. They compute every 6 hours a new computation, and you can also, if you look a bit around on the internet, find predictions and use that. Then I think rather recently, but probably exists already a couple of years, there's also WRF, a weather research and forecast model simulation tool. So if you have a lot of time, you can do really nice stuff. It's used to simulate hurricanes or mountain weather or doing forecasts yourself. But you need a big computer. And some of the weather sites, they provide this information. Wettercentrale, DE is an example. But also in our community, the Desert Fireball Network, they run WRF code to provide a model at the moment that the fireball is appearing. Now the open data is general, not very detailed compared to balloons at least, and it is in the open on the internet difficult to find data above 15 kilometer altitude, and that is not sufficient for our work. So let's look a little bit deeper into this. I use as a trigger the fireball over the Netherlands June the 4th. That was also the idea that we want to look into that. That was just a fireball which happened. You are at breakfast and there are already results from the different groups. Here's just an ensemble of what all is computed by at least 3 different networks. This is a fireball which maybe have created a meteorite, but there's a discussion about that, but it's also not important for my talk. I spotted with this fireball that we all use also different. We just grab some weather data and we start computing, and that started thinking, but can we do that? So we looked around. So this is a set of all the stations around us. The red arrow is where the trajectory of the fireball is, and the closest weather station is De Beeld in the Netherlands, which is in the center. And the second closest is Essen, and then the rest is further away, about 100 kilometers or more. So I compared some of the data. Here you see an ensemble of different weather stations, weather balloons, pressure and temperature, and you clearly see they measure exactly the same. So I think for my talk, we can skip this. This is under control. It doesn't matter so much what data you take. Then we look at the wind. Here's at the left wind speed, at the right the wind direction, vertically the altitude, and horizontally the parameter. There you see it's not all the same. So you see the dots are measurements. The blue one is the WRF model run by the DFN network. And what you especially see is that they compute in a higher wind component at about 10 kilometers. That's where normally the jet streams are, and the sounding stations, they don't compute that. That's the main difference. For the rest, it is pretty much the same, I would say. If you look then, there's another day, but if you don't look then at models, various models, but at the same location at the same time, you also see that there are differences. So I'll go a bit quick. Here you see the wind strengths for two different sites, the weather centrale and model centrale, and at the bottom I have used the ECWMF, and you see that yeah, it is more or less the same, but it's absolutely not identical. Both in strengths and directions, there are differences between the models taken at the same time, made at the same time, same location. So that puts a question mark. So what data to take is then the big question. So that triggers a nice computing example. Compute a dark flight for a single fragment, and use the different weather data sets and just see what happens. I used again the 4th of June fireball. As a trajectory, I took the Oscar 7 one, and I used for this example two different fragment sizes. Now, here you see the result. The blue is the trajectory of the fireball. The white spots are in 16-gram fragments, and in yellow you see a smaller fragment. You see immediately there is a variation, so it depends which data set you take. You see also that if the fragment is smaller, that the differences are bigger. It's clear. It's a smaller fragment, slows down earlier, it travels longer in the atmosphere, so the wind has more grip on it. But you also see the little bit larger dot here, that is the model, the rest is sounding data. These ones are close to the trajectory, the others are a bit further away. And you note that the model is not coinciding with the sounding data. So this shows already there is, well, it is not trivial. 1 kilometer is roughly as a size indicator. And how does that compare then? Is that a lot? Now for the meteorite hunters, I think they have a better grip. But understanding what it is, here I have overplotted a dark flight computation is done by Dennis Vida, and it gives, I think, a nice comparison. The size of this is due to the inaccuracy in the trajectory, and you see that the weather station differences are in the same order as what the accuracy in the data set is. So I think this is something you cannot neglect. And then in the note which I have given here below, we know from the weather services, we asked them, and we did some study, this particular night was a very quiet night. So they said it does not so much matter which station you take, at least within 100 kilometers. So that's certainly true for Essen and De Beeld. There were no jet streams. they figured out. And even more peculiar, at the time, the weather balloons were in the air at the moment the fireball appeared. So this is a kind of an ideal data set. So in practice, I think it can even be much worse. So the upshot is that it is important to look at which weather data you take. There is a difference between model data and sounding data. Sounding data is much more detailed. We found a spread of in the order of 1 kilometer for 16 gram fragments, of course. And it is not so trivial what to take. I would say in this case, we would take a kind of weighted average between the different sounding stations with a waiting time, which is easy because it was all the same here, and a geographic location. But I think you have to be very careful and also look in specific cases, also if there is some more dynamic effect, mostly caused by jet streams, which can locally vary and quickly in time. And for that, I believe model data is good to look at. We are no weather experts, so expert input is always welcome. Thank you.